I welcome you all for the sixth session of Quantum Mechanics Part 2, which belongs to BSc Physics for the sixth semester, paper 8, for all the three Bengaluru universities. This is Narayan Sharma, so from Government Festival College Part 2. So in this session, I would like to discuss about the second application of Schrödinger's equation, time independent equation, and that one is particle in a three-dimensional box. We have already discussed particle in a one-dimensional box. Actually, here we are extending so our idea to a particle in a three-dimensional box. In the last session, I discussed about quantization of a particle which is trapped in a one-dimensional box. Here we are discussing about a particle which is trapped in a three-dimensional potential box, which is surrounded by a infinite potential region, so that the particle cannot exist outside the three-dimensional box. So therefore, in order to discuss this one, let us see the objectives of this particular session. So the first objective is definitely to apply Schrödinger's equation to a particle in a three-dimensional box. We're going to write down Schrödinger's equation to the particle in a three-dimensional box. Of course, once we are able to write a Schrödinger equation, so it is possible to solve the Schrödinger equation. So therefore, it is possible to get expression for the energy eigenvalues. And also it is possible to calculate the wave function of the particle, which is trapped in the three-dimensional potential box. Here, we shall try to understand one more concept, that is what we call it as degeneracy. So for example, we say some of the energy levels of the particle which is trapped in a three-dimensional box is a degenerate energy levels. So what are those degenerate energy levels? What is the degeneracy? Degeneracy we shall try to understand. So this is our second application of Schrödinger's equation. Here we are considering a particle of mass m restricted to travel in a rectangular box of sides Lx, Ly, and Lz. So the sides being infinitely hard and parallel to xyz axis respectively. In our previous discussion, in the previous session, so the particle was restricted to move along x-axis between x is equal to 0 and x is equal to L. We are extending the idea and we are assuming that the particle is restricted to move not only along x-axis but along y-axis and along z-axis also. So therefore, I can say that along x-axis, the particle is restricted to travel between x is equal to 0 and x is equal to Lx. Along y-axis, the particle is restricted to move within the region y is equal to 0 and y is equal to Ly. And along z-axis, z is equal to 0 and z is equal to Lz. So therefore, here we have a particle. The particle is restricted in a rectangular box whose sides are Lx, Ly, and Lz. So we have a particle here which is trapped in a three-dimensional potential box, where again we are going to assume the potential energy of the particle to be 0. And outside the box, the potential energy is infinitely large, so that the particle cannot exist outside the box. So that's why we are calling this one as a particle in a box, three-dimensional case. So we have a particle which is trapped in a three-dimensional box. It cannot escape outside the box. It is because in order to escape, it has to have infinite amount of potential energy, and that is not possible. So therefore, the particle is restricted within the box of three dimensions. So where each of the box sides are Lx along the x-axis, Ly along the y-axis, and Lz along z-axis. So as the particle is free, the potential energy of the particle is 0. Without loss of generality, we can assume that the potential energy of the particle to be 0 inside the box. So therefore, we can write the Schrödinger's equation for such a particle as, since we are dealing with the three dimensions, we have two more extra terms apart from dou square psi by dou x square. So therefore, the equation becomes dou square psi divided by dou x square plus dou square psi divided by dou y square plus dou square psi divided by dou z square plus 2me E divided by h cross square So psi is equal to 0 as potential energy of the particle is 0. So this is basically a second order partial differential equation which has to be satisfied. So it is possible to find out the exact solution using the boundary conditions. We shall do it one by one. So this above equation can be written as, so for the sake of simplicity, we have taken 2me by h cross as k square as we did in the previous session. So therefore we can write this equation as dou square psi divided by dou x square plus dou square psi divided by dou y square plus dou square psi divided by dou z square plus k square into psi is equal to 0. Where k square is nothing but 2me by h cross square. So now in order to solve this equation 2, we are adapting a standard method. That is what we call it as separation of variables. This whole wave function psi is a function of x comma y comma z. This whole wave function psi, which is a function of x comma y comma and z coordinates, can be treated as something like a product of three different functions. So psi is a function of x, capital X, which is a function of x coordinate. So psi is a function of y, which is capital Y, which is a function of y coordinate. Similarly, it is a function of capital Z, which is a function of z coordinate. So here, so the dependence of psi on x, y, z, we have split that one into three different components, and each component so being the function of each coordinate only x comma y comma z. So therefore capital X, capital Y, and capital Z give us so three different functions which are so functions of x coordinate, y coordinate, and z coordinate respectively. So therefore we are able to separate the three variables, x variable, y variable, and z variable separately. So that's why this method is what we call it as so separation of variables method. Now if I differentiate this equation 3 with respect to x twice, then I'm going to get the dou square psi divided by dou x square, y z into dou square x divided by dou x square. So where y and z, since y and z are functions of y, so small letter y and small letter z, so therefore they have to be treated like constants. So therefore they need not have to be differentiated. So therefore dou square psi divided by dou x square becomes y z into dou square x divided by dou x square. Similarly, we are going to get the second term, dou square psi divided by dou y square is equal to x z into dou square y divided by dou z square, and dou square psi divided by dou z square is equal to x into y into dou square z divided by dou z square. This is what we call it as equation 4. So this is a simple differentiation. So we are getting three different terms. And also in the previous equation I mentioned, so there was a k square term here. Since k square is a vector quantity, so that the vector quantity k square can be written as in terms of three different components. So kx square plus ky square plus kz square. Then kx is the component of the propagation vector along x-axis. Ky is the component along y-axis, and kz is the component along z-axis. So therefore, by substituting this equation 4 and equation 5 into our previous equation 2, substituting equation 4 and equation 5 in this equation 2. So once we do that, we are going to end up an equation something like this: y z dou square x divided by dou x square plus x z dou square y divided by dou y square plus x y dou square z divided by dou z square, plus in the place of k square we have written kx square plus ky square plus kz square, and of course so psi we have replaced with x y z is equal to 0. This is what the equation. And if we divide this entire equation 6 by x y z, capital X, capital Y, and capital Z, so the three different functions, then we are going to get 1 by x into dou square x divided by dou x square. So I have taken this so kx square term along with this first term. So therefore 1 by x into dou square x divided by dou x square plus kx square plus 1 by y into dou square y divided by dou y square plus ky square plus 1 by z into dou square z divided by dou z square plus kz square is equal to 0. So this is equation 7. So we have got equation 7. So just by dividing the equation 6 by capital X, Y, Z, the product capital X, Y, Z. So we are going to get this kind of equation, that is equation 7. Now this equation 7, there are three different equations here. We have three different terms here: 1 by x into dou square x divided by dou x square plus kx square. Similarly, we have 1 by y into dou square y by dou y square plus kz y square plus 1 by z into dou square z divided by dou z square into kz square. So we have three different terms. And we have to observe that each term is a function of one coordinate only. For example, this first term, what I am showing here, it is a pure function of x coordinate only. And the second one is a pure function of y coordinate only. The third one is also a pure function of that coordinate only. So therefore, since we have three different terms which are independent of each other, so the conclusion is, so each one has to be E0. I mean, this whole equation would be 0. This whole equation 7 would be 0. Only when each term in the bracket, first term and the second term and the third term separately, when they are 0. So only then this equation 7 is satisfied. Otherwise, equation 7 cannot be satisfied. Once we do that, so then we are going to get three different equations. So dou square x divided by dou x square plus kz square, kx square into x is equal to 0. Dou square y divided by dou y square plus ky square into y is equal to 0. And dou square z divided by dou z square plus kz square into z is equal to 0. So we are able to divide this equation 7, which is consisting of three different terms, into three different equations. Equation 8, equation 9, and equation 10. And these three equations are familiar equation in the sense these three equations resemble the equation that we have already discussed in the case of a particle trapped in a one-dimensional box. So therefore, finding out the solution of each equation is very simple, and it is a known method what we did in the previous session. So therefore, for the sake of continuity, I am going to mention the solution of equation 8. So just by changing the terms, so it is possible to obtain the solution of equation 9 and solution of equation 10 also. We need not have to write down the solution of 9 and 10 separately. So if we just try, if we are able to write the solution of equation 8, then it is possible to combine all the three solutions to write the general solution of the equation. Now this equation 8 has a solution of the form capital X is equal to ax sin kx into x plus bx into cos kx into x. So equation 11 represents the general solution of equation 8. Now there are two boundary conditions. One is the function capital X is equal to 0 for x is equal to 0, and the function capital X is equal to 0 when x is equal to Lx also. That is what the boundary along x-axis within which the particle is restricted to move. So therefore, the wave function, capital X must become 0 at x is equal to 0, and the wave function capital X must become 0 at x is equal to Lx also. If you substitute, precisely this is the same thing what we discussed in the previous session. There is a particle trapped in a one-dimensional box. So then we are going to get the solution of equation 8. Remember, this is equation 8. The solution of this equation 8 after putting the boundary condition is something like this. Capital X is equal to ax sin nx pi divided by Lx into x. This is equation 12. So we had two more equations, equation 9 and 10. So similar solutions can be written for equation 9 and 10. So therefore, I have mentioned here. So solution for equation 10 is capital Y is equal to ay sin ny pi divided by Ly into y. And solution of equation 11 is z is equal to az sin nz pi divided by Lz into z. Here, instead of one quantum number n, we have three quantum numbers nx, ny, and nz. So nx is the quantum number along x-axis, ny is the quantum number along y-axis, and nz is the quantum number along z-axis. And each of these can take discrete set of values 1, 2, 3, 4, 5, etc., just like in the previous case. Now, please remember, I mentioned here, so wave function psi, the total overall wave function psi is a function of capital X, capital Y, and capital Z. So therefore, here we have three solutions: solution for X, solution for Y, and solution for Z. And if you multiply equation 12, equation 13, and equation 14, we are going to get a complete solution, complete wave function of the particle which is trapped in a three-dimensional box. So therefore, psi becomes equal to capital A, capital X, capital Y, capital Z. And if we multiply equation 12, 13, 14, we are going to get ax, ay, az into sine of nx pi divided by Lx into x, sine of ny pi by Ly into y, sine of nz pi divided by Lz into z. Otherwise, this equation also can be written as, so a times sine term, sine of nx term, sine of ny term, and sine of nz term. What we did is, we have taken these three constants ax, ay, az as capital A. So this capital A is actually the normalization constant for this wave function psi, which is actually a product of three different constants ax, ay, az And it is possible to combine these three and make it as a single constant. So therefore, equation 15 represents the solution of the wave function provided capital A, the normalization constant, has to be found out. Okay. So since the particle is existing within the boundary of the three-dimensional potential box, so therefore the overall probability of finding the particle anywhere inside the box is equal to 1. So therefore we can use the normalization condition that if we integrate this modulus of psi square with respect to x, with respect to y, with respect to z. So once along x-axis, once along y-axis, and once along z-axis, between the limits 0 to Lx, 0 to Ly, 0 to Lz respectively, that must be equal to 1. So I'm avoiding all the mathematics here. If you substitute this equation 15 in equation 16, what we have to do is we have to square this equation 15, we have to square this, and we have to substitute in the equation 16. And we have to do three integrations separately, once with respect to x, once with respect to y, and last again once with respect to z. And if we do the simplification, then we're going to get the constant value a as a becomes equal to a divided by lx ly lz whole to the power of 1 by 2, or a divided by this product lx ly lz is nothing but the volume of the potential box. Okay, it is like three sides of a cube, three sides of a rectangular box. One of the side has a length of x. The second side has a length of ly, and the third side has a length of lz. So therefore, this product lx ly lz actually gives the volume of the box. So therefore, we can write capital A normalization constant to be equal to 8 divided by v whole to the power of 1 by 2. This can be calculated using this simple integration. So as per equation 16. So therefore, we can substitute the value of a back into our equation. So 15, and once we substitute, we are going to get, so the complete wave functions are, they're also called energy eigenfunctions. So please remember these functions, wave functions are also called as energy eigenfunctions. So these are the energy eigenfunctions for a particle in a three-dimensional box. Okay. So it is actually given by psi is equal to 8 by v whole to the power of 1 by 2, sine of nx pi x divided by lx, sine of ny pi y divided by ly, sine of nz pi z divided by lz, equation 17. So therefore, we are able to find out normalized wave functions of a particle trapped in a three-dimensional potential box of volume capital V. So these normalized wave functions are given by equation 17. And please, you have to make sure that we have three quantum numbers here. Unlike one quantum number in the case of particle in a one-dimensional box, we are getting so three quantum numbers. So nx quantum number along x-axis, ny quantum number along y-axis, and nz quantum number along z-axis. And all these quantum numbers nx, ny, and nz, they can take the possible values of 1, 2, 3, etc., etc. 0 is not allowed. So therefore, this equation 17 actually represents, so the equation representing energy eigenfunctions of a particle, so which is trapped in a three-dimensional potential box, outside which the potential energy is infinite. Now it is also possible to find out the energy eigenvalues. So the energy eigenvalues are given by, we can show this one very easily. So by combining three different equations. Okay. So here we have to use the equation. Let me show here. Here we have to use this equation k square is equal to kx square plus ky square plus kz square. We all know that k square is equal to, so k square is equal to 2me by h cross square. So therefore 2me by h cross square, k square is equal to kx square plus ky square plus kz square. And the value of ky, kz, they are actually equal to nx pi divided by lx. The value of ky is ny pi divided by ly. The value of kz is nz pi divided by lz. We can substitute all these things, and it is possible to find out the energy eigenvalues. The energy eigenvalues of a particle trapped inside the potential box is given by E. Clearly, E is a function of nx, ny, and nz. So therefore, E of nx, ny, nz is given by pi square h cross square divided by 2m into nx square divided by lx square plus ny square divided by ly square plus nz square divided by lz square. So therefore, equation 18 represents the energy eigen functions of a particle which is trapped in a three-dimensional box, where nx is equal to 1, 2, 3, etc. ny is equal to 1, 2, 3, etc. and nz is also equal to 1, 2, 3, etc. Lx, Ly, and Lz are the length of the potential box along x-axis, y-axis, and z-axis respectively. So therefore, we can say that instead of this energy, instead of only is depending on not only depending on one quantum number, in the case of particle in a one-dimensional box, we require 3 quantum numbers. So we had something like an expression pi h cross square divided by 2m into n square by l square in the case of particle in a one-dimensional box. But here, instead of one single quantum number n, we have three quantum numbers nx, ny, and nz. So therefore, we need to consider three quantum numbers in the case of particle that is trapped in a potential box. So this is what the expression for the energy eigen. Now, let us try to understand this concept of degeneracy. I have already told, so nx and ny and nz can take our possible values starting from 1 to 3, etc., etc., etc. Now the thing is, if I substitute nx is equal to 1 and ny is equal to 1 and nz is equal to 1, that this is what the least possible value possible for your nx and nz. Nx and ny and nz, they can take the least possible values of 1, 1, 1. So therefore, if I substitute here in this particular expression, nx is equal to 1, ny is equal to 1, and nz is equal to 1, then I'm going to get the energy of the particle. So in the least energy state, and that least energy state is the ground state. So therefore, the conclusion is the ground state actually corresponds to nx, ny, nz. They are being equal to 1, 1, 1. All the three values becoming 1. Now, if I go to the excited state, for example, I can give the next possible level after ground state is what we call it as the first excited state. So in the case of first excited state, so out of these 3 quantum numbers, any one quantum number has to take a value of 1, and the other 2 quantum numbers have to take a value of, any one quantum number has to take a value of 2, and the other 2 have to take a value of 1 and 1. For example, if I go for the pair nx, ny, nz, that is equal to 2, 1, 1, 1, where nx is equal to 2, ny and nz are 1. Or it is also possible that nx and nz are 1 and ny is 2. Or it is also possible that nx and ny are 1 and nz is equal to 2. So this is what the next possible state. So for which, so the first excited state has a same energy. Now, if I substitute this value of either 2, 1, 1 or 1, 2, 1 or 1, 1, 2, for example, if I go for a special case where Lx is equal to Ly is equal to Lz, that is what we call it as a cubical box. Okay. So if all the 3 sides of the potential box are equal, that means if Lx is equal to Ly and Ly is equal to Lz, then that box is what we call it as a cubical box. In the case of a cubical box, this L square, this becomes Lx square, this also becomes Lx square, and this also becomes Lx square, and this Lx square can be taken outside. So therefore, this energy is now dependent only on nx square plus ny square plus nz square. But if I'm going to substitute 2, 1, 1 or 1, 2, 1 or 1, 1, 2, I'm going to get the same energy here. So therefore, for 3 different possible values of the quantum numbers, 2, 1, 1, 1, 2, 1 or 1, 1, 2, we are going to get same energy. Whereas if I'm going to substitute 2, 1, 1, 1, 2, 1 and 1, 1, 2 in the expression 17, so the 3 wave functions are not the same. I'm going to get the 3 different wave functions for nx, ny, and nz becoming equal to 2, 1, 1, 1, 2, 1 or 1, 1, 2. Whereas I'm going to get the same energy here in this particular expression if nx and ly and lz are equal, such that their energies are becoming the same. So therefore, we can say that, so we have the first excited state, which corresponds to either 2, 1, 1 or 1, 2, 1 or 1, 1, 2, is what we call it as a 3-fold degenerate. Ground state is not degenerate. It has a 0 degeneracy, whereas the first excited state corresponding to 2, 1, 1, 1, 2, 1 or 1, 1, 2 has 3 different functions, 3 different wave functions, but all the 3 different wave functions, all the 3 different states will have the same energy. So such a thing is what we call it as degeneracy. So therefore, we can conclude it is possible to observe a concept called a degeneracy So in the case of a particle which is trapped in a cubical box where Lx, Ly, and Lz are equal, such that if you go to the case of first excited state, so there are three different states corresponding to 211, 121, or 112, and all the three states would be having the same energy. So this concept, this idea where different energy levels, different states, different wave functions having same energy is what we call it as a degeneracy. For example, here, so our particle which is trapped in a cubical box has threefold degeneracy. So for the first excited state, and the different second excited state and third excited states will have different numbers of degeneracy. So anyhow, this is what the thing about degeneracy we wanted to discuss, and we have discussed. And just I would like to come back here. We have successfully discussed two applications of the Schrödinger's equation. So the first one is particle trapped in a one-dimensional box. I covered this one in the previous session. In this session, I successfully tried to cover the particle that is trapped in a three-dimensional box. So we are able to write Schrödinger's equation. We could actually solve them so that in order to find out the energy eigenvalues and the energy wave function, energy wave functions of the particle. And here automatically there comes a picture that we call it as a degeneracy. So therefore the particle energy is degenerate if you go to higher energy levels like first excited state and second excited state for a cubical box and so on. So I'm going to end my session here. I thank you all.